Thanks for adding the agenda into the chat. Um,
No
so
problem.
for those who, everyone attending, if you are interested in the agenda, you can open up the chat. There's also a Q&A option under the chat, I believe. And so I'll go over this in a little bit, but if you have questions, we're going to save questions until the end after we have finished our presentations, and then it'll be hopefully about 15-20 minutes of discussion and Q&A. So please put your questions into the Q&A, and that's what we'll be monitoring. We probably won't be monitoring the chat for the Q&A. So just a heads up. Although I don't know how to look at the Q&A. Oh, there it is. Okay. A lot of options. Okay. Well, it is 3 minutes past the hour, so I think we will get started. Thank you, everyone, for attending our kickoff webinar for the BGC-Argo webinar series. This will be an approximately quarterly webinar, and it's hosted by the GO-BGC, the Global Ocean Biogeochemistry Array, which is a NSF Mid-Scale Research Infrastructure program that's funded to deploy 500 biogeochemical profiling floats globally over the next 5 years, and also by the U.S. Ocean Carbon and Biogeochemistry Program. And big thanks to them for hosting this webinar series. It's hugely helpful and allows us to reach the wider community. OCB is funded by NSF and NASA. So thank you, everyone, for joining. And then so before we get started, I kind of want to just introduce the organizing committee for this webinar series. So we are all on video right now. And then so the video, we'll turn off the video in a little bit to improve bandwidth. But it's organized by Natalia Scripps, myself at MBARI, Jonathan Sharp at NOAA PMEL, Alison Gray at University of Washington, Channing Prend at Scripps, and also Yubin Huang at NOAA PMEL. And we are, we're kind of new to all of this, and we really want this to be, engagement with the community. So any feedback, please email us. There is a listserv that you can email to, GO-BGC OCB webinar at listserver.mbari.org, and that email will go to all of us. So yeah, we want to hear from you, so please send us feedback. And so I wanted to kind of go over like the overarching goal of this webinar series, and really the goal is to inspire you as a scientific community to use BGC-Argo data. Currently, there are 450 active floats. This is a map that you can download, you can create on OceanOps, and then all of these floats data are QC'd in real time and are freely available for anyone to use, and no strings attached. So it really is an opportunity. We truly believe that it will transform how we observe biogeochemical cycles in the ocean, and it really is an opportunity to do novel and creative science with this really powerful emerging data set. And then so our goal is to inspire you to think about new creative ways to use this data, and also to equip you with kind of the tools and also the planning, and keep you updated with where profiling floats are projected to get deployed over the next years. And so to do this, we basically are going to, each webinar is going to have a science theme, and then so we will highlight emerging science that uses BGC-Argo data with a focus on early career researchers. So again, if you have topics that you would like to see covered, or you want to present in one of these webinars, please email us. And so the first science webinar will happen in July of 2022. And today, since this is a kickoff webinar, we aren't going to focus on science, but it's going to focus more about introducing this program, GO-BGC and BGC-Argo. So today's agenda, we're going to do an introduction to BGC-Argo and GO-BGC, followed by upcoming float deployment locations over the next several years, and then going to where and how to access BGC-Argo data, and then finish that with data, how BGC-Argo data are adjusted, and then the resultant quality of this data set. And then we will go into the discussion and Q&A. So without further ado, it's Alison's turn to tell you about BGC-Argo and GO-BGC. So stop the video.
Okay, great. Thank you, Yui, and thank you all for joining today. So it's my pleasure to be able to give a brief introduction to BGC-Argo. Many of you probably are already very familiar with BGC-Argo and GO-BGC, but some of you may be new to this program. And so I wanted to spend a few minutes just kind of talking about how we got here, and then also a bit of the future outlook in terms of where we're deploying floats in the upcoming few months, in the upcoming year, and so that you, if you'd like to use the data, know kind of what's on the horizon. Okay, next slide. Thanks. Okay, so BGC-Argo, or Biogeochemical Argo, is a component of the Global Argo program. So if you don't know what the Global Argo program is, I have just a few little figures here to show, kind of give a introduction. Essentially, the Argo program is an array of profiling floats. A schematic that's shown on the left kind of gives you an idea of how the floats operate, and the core Argo program, as we call it, is dedicated to measuring temperature and salinity. You can see an example profile there in the middle. And then the figures on the right, which come from this really nice review paper, Johnson et al. From 2022, show kind of the revolutionary nature of the core Argo program in terms of measuring temperature and salinity in the subsurface ocean over the past 2 decades. So the top figure on the top is showing you the World Ocean Database of all the profiles, and it's colored by each 1 degree by 1 degree grid box is colored by the number of profiles that extend, I think, deeper than 1,000 meters in the World Ocean Database, starting, for all time. And then the figure on the bottom is showing the same image, but for the Argo database. And so you can see just the stunning, expansive coverage that the Argo program has allowed us to get for physical parameters such as temperature and salinity. Next slide. And so, kind of inspired by this success of the Argo program, and and inspired by the capability of these platforms to carry additional sensors, the Biogeochemical Argo program is an extension of the Argo array of profiling floats to include floats that are equipped with 6 biogeochemical sensors. These are pH, oxygen, nitrate, chlorophyll, suspended particles or backscatter, and then downwelling irradiance. And so the map that you're seeing here, which is I think the same one that Yui showed, is just showing you kind of the current distribution as of actually last month of active floats that are measuring 1 or more of these parameters. Many of these floats, if you look carefully, you'll see are actually just measuring oxygen. So that's a sort of an easier measurement to make, and for many, and we've been doing it for a lot longer, and so many floats are equipped with just oxygen, but the Biogeochemical Argo program's goal is to sustain this, or to build this array for all 6 of these parameters. And next slide. And so goals that sort of questions that we can start to look at with a global distribution of floats measuring these 6 parameters, and are really many, too many to list here, but just some examples are questions concerning carbon cycling, oxygen minimum zones, nutrient fluxes, ocean acidification, the biological carbon pump, phytoplankton, phenology, and primary production. And then, of course, the impacts of this array really will provide transformative information for the management of living marine resources, carbon budget verification, and operational ocean models. And next slide, please. So this Biogeochemical Argo program is really an extension, like I said, of the very successful Argo program, and this is all kind of comes together as part of what we call the One Argo design for Argo for the next 20 years. And it really includes 3 elements. One is expanded coverage of the core measurements in the polar sea ice zones and the marginal seas. Second is increased regional resolution in western boundary currents and equatorial regions. You can kind of see that in these green shaded areas on the map. And then the third is 2 major extensions of the Argo mission. one to sample biogeochemical parameters, and then of course the deep Argo mission to sample below 2000 decibars. So I just want to emphasize that biogeochemical Argo is really one component of this larger global observing system. Next slide. Thanks. Oh, okay. And as such, the linchpin, if you can go back. Yeah, thanks. The linchpin for this one Argo design is that the BGC and deep Argo floats are providing core parameter, core temperature and salinity profiles as well. And so they're doing that on a 10-day cycles, profiling to at least 2000 decibars and parking at 1000 decibars. Okay, next slide. So a little brief history of BGC-Argo, and this is definitely not comprehensive. It's very abbreviated and kind of a little bit of a US focus, but I just want to I thought it would be good to see kind of where we're coming from in building this global biogeochemical float array. So in the 80s and 90s, there was really the groundwork was laid for just the development of profiling floats partly through WOS. And then in the late 90s, we had development of the Argo implementation plan, and that really kind of kicked off in 1999. Next. Pretty quickly thereafter, we had the, first biogeochemical sensors being added to floats. So in the early 2000s, we had a PAR sensor as well as optical measurements being added to profiling floats, and then followed by 2 different types of oxygen sensors and bio-optical sensors as well. Next slide. At the roughly 7 years or so after the implementation of the global Argo array began, the Argo program reached its target global coverage of 1 float every 3 by 3 degrees. So that was a big monument in the history of Argo. Around the same time, had sort of a more coordinated community efforts to really realize and explore the prospects of adding oxygen sensors onto profiling floats, as well as the first nitrate sensor was deployed on a profiling float in 2007. Next slide. In 2009, there were a few seminal kind of workshops and meetings and white papers that were put together by the community to really start to explore the idea of a global array of biogeochemical floats. Next slide. And in 2013, the first pH sensor was deployed on a profiling float near Hawaii. And shortly thereafter, the SOCOM program was started in 2014, and with a goal of deploying 200 BGC floats in the Southern Ocean over the course of 6 years. Next slide. And then that kind of a few years after that program started, a large group of people from a number of different countries met and developed the Biogeochemical Argo Science and Implementation Plan, which is really a guiding document for the global biogeochemical Argo array. It called for 1,000 profiling floats with 6 parameters, and just like the core Argo program, the data are all freely available in near real time. And the implementation plan calls for the US to provide roughly half of the global array of BGC floats as we do for the core Argo array. Okay, next and final on my timeline. So that kind of leads us up to more recent years, and in 2019, the One Argo program, or sort of design goal, was really formally adopted, and in 2020, GO-BGC was started, which is, as Yui introduced here, the Global Ocean Biogeochemistry Array funded by NSF to deploy 500 floats globally. Okay, and then in 2021, SOCOM was renewed as well. So moving kind of gets us to the current stage where we have now 4 different commercially available profiling floats with chemical and biological sensors. The Navis from Seabird, Apex from Teledyne, Webb and Provor from NKE in France, and the BGC Solo 2, which just is coming on the market from MRV. And these floats all are equipped to carry the six biogeochemical sensors, 5 or 6. They're with ongoing development efforts to add 6 sensors to the Apex, for example, and just showing you some examples there of the one type of optical oxygen sensor, and the nitrate and the ISFET pH sensor, which also has some recent design improvements to improve manufacturability and reliability. Next slide. And then the optical sensors that measure chlorophyll fluorescence, backscatter, as well as downwelling irradiance. Okay, next. So there's really been, even though we're kind of in the early stages of this global array, there's been already a wide array of papers that have used this data and have really made important advances in understanding of all these different topics. It's too many to really talk about here, but we're hoping to, as Yui said, feature some new and upcoming. You can go. That's fine. New and upcoming science in the next webinars, but just to give you an idea of how this data is being used, it's really papers per year that are using BGC-Argo data has really just grown exponentially in the last 5 years. And so we're hoping to continue to see more and more use of this data. Okay, next. So I mentioned SOCOM before. If you haven't heard of this, it's the Southern Ocean Carbon and Climate Observations and Modeling Project, which was a pilot array for the global BGC-Argo array in the Southern Ocean, and was started in 2014 and is going currently through 2024. To date, we've deployed 217 floats that have oxygen, pH, nitrate, and bio-optical sensors. If you go to the next slide. The GO-BGC array, as we've already mentioned several times, is sort of building on the success of SOCOM, and with a goal of deploying 500 BGC profiling floats globally over the next 5 years. We've deployed 62, I think something's blocking my screen, but I think it's 62 deployed GO-BGC floats will have been deployed through April of 2022. We recently had our 1-year anniversary of the first float deployment. That happened just a few weeks ago. And we are deploying 5 and 6 sensor floats, and the partner institutions are MBARI, UW, Scripps, Woods Hole, and Princeton. And you can see there the current floats that we have deployed, current distribution. Next slide. Oh, that's just our website has much more information, and so gobgc.org, and you can find the data and many tools for using the data, as well as much more information. So next slide. At the website, you can also find data that not just from GO-BGC, but we're trying to make available data from some SOCOM, as well as other partner floats that are processed through MBARI. And that's just, this map is just showing you the current sort of data distribution of that data set. Those data are also available through the Argo GDAX. Next slide. Presently, our outlook for deployments in the US is kind of listed here in this table, and as you can see, goes out through 2025, and we are in 2022 here deploying about 117 floats, and through GO-BGC, SOCOM, as well as other floats funded by NOAA, the NOAA program in the US, and as well as NASA. And then ramping up our GO-BGC production for in the next few years. Next slide. So where these floats are going. So in the more sort of immediate term, this map is showing the floats that are going in the next few weeks. And the ones that have just been deployed are shown as open circles, and then the dots are the planned deployments that are happening. And so those data will be, once the float's deployed, the data start coming in, like I said, in near real time and are available. And then if you're thinking about more future, if we look at the next slide, we'll see sort of a year 2 outlook for GO-BGC deployments. And we see that there's a number of different cruises that we're targeting to deploy floats on, and as well as sort of planned lines, as well as sort of areas of operation where we are hoping to or looking at deploying floats. And so this is just for the US contributions from GO-BGC and SOCOM. Of course, our international partners in the BGC-Argo program are also deploying floats. So if you go to the next slide, we have over 200 or roughly 250 floats over the next 5 years that are being deployed from international partners, which are listed here. And many different countries are very active in ramping up their efforts in the GO-BGC, in the BGC-Argo program. And if you click on, I think one more time, it'll show you kind of the general areas where the partners, where these countries have their plans for deployment in the next upcoming years. So hopefully that information will be helpful if you're thinking about where you might be able to find BGC-Argo data in the coming years. And of course, we're always looking for float deployment opportunities. So if you have cruises or of good opportunities, please reach out and let us know. I think that's all I had. So I'm going to turn it over to John next.
Thanks, Alison. And I just want to quickly mention that, the floats from the previous, the US contributions and these 250 floats from our international partners are all 5 or 6 sensor floats. So they will, they'll have most of the BGC sensors on them. So that really, by co-locating all the sensors on a single float allows us to do a lot more science with them. So thank you, Alison. That was wonderful. John.
Okay. Let's see. Okay, I'm going to assume you can see this all right. So I just wanted to share some info about how to access biogeochemical Argo data, the types of files that you'll find once you go to access the data, and then some tools that can help you with data access and visualization. So first of all, data access. The Argo Global Data Assembly Centers are the primary access points for BGC-Argo data. Coriolis and US GODAE. So these two are mirrors of each other, and they hold all of the Argo data that's available, as well as biogeochemical Argo data. And so the data is served via FTP, HTTP, rsync, digital object identifiers, and through a variety of secondary data servers, which I'll talk a little bit about. But the main hubs for the data, again, are those global data assembly centers. And so the types of data files that you'll find when going to access BGC-Argo data. First of all, profile data files. So these are netCDFs that contain data from each of a float's individual profiles. And you'll see the naming convention here, either a core data file, which won't have a first letter, file with biogeochemical parameters, or both interpolated to one pressure axis. And that'll have an S. And then these are both available as real-time quality controlled data files, as well as delayed mode quality controlled files, which I think Yui will discuss a bit more. You'll also find data files containing all cycles. So these have data from all of the floats profiles, interpolated onto one pressure axis. The prof is the core parameters, and the sprof will contain the BGC parameters as well. You can also find metadata files for each individual float containing trajectory information, different types of metadata, and technical information. These index files can be really useful. So these are contained kind of in the main repository of each GDAC, and they contain information about float positions, dates of deployment and profile dates, institutions that are responsible for each float, sensors that are available, parameter data modes, and other types of metadata. So these can be useful when you're kind of looking at which floats to actually use data from. And you'll also find in the GDACs auxiliary files containing technical information and engineering data, as well as this gray list, which has information about bad or potentially bad sensors on specific floats. So I'm going to quickly run through just a few different tools that can help with data access and visualization. This is not an exhaustive list. There are definitely some other tools out there, but these are some that I found useful. And also these are tools that are listed on the GO-BGC webpage, so you can find links and descriptions of these upcoming tools on that webpage. So one of those is MBARI FloatViz. So with this, you can plot profiles and download simple data files from individual floats. NOAA AirDAP allows you to subset and download Argo data, including BGC-Argo, and also to make graphs and different types of plots. The GO-Argo dashboard is really helpful for visualizing float positions and trajectories, as well as float data, and for downloading data files. ArgoViz from the University of Colorado is also really helpful in terms of visualizing float positions and plotting profiles and downloading data files. In the UCSD data archives, you can download snapshots of SOCOM floats, or as Alison showed before, GO-BGC and floats processed through MBARI. And you can also download derived carbon parameters from this data source. Ocean Ops, you've seen a couple of these maps, so these are really, this website's really useful in terms of visualizing the status of the Argo array, the BGC-Argo array, and other observing systems. These float status tables, these are available through SOCOM, through GO-BGC, and a number of other programs. And these are sortable tables that can help assess float status, and they include data links as well. And the last tool that I'm talking about here is these fairly newly available BGC-Argo float toolboxes. So these are available in R, MATLAB, and Python. And these allow you to subset and download BGC-Argo float data, and also to create a number of various plots. And I'm going to turn it over to Hartmut Frenzel, who's going to talk a little bit more in depth about how to use these BGC-Argo float toolboxes. I will stop sharing if I can.
Geht on. Okay, so John just ended on our toolbox that we have developed to make it easy for you to access and visualize this data. Our motivation was that the organization of the files and the GDACs is nice for computer, but especially if you don't know which float ID you're looking for, it would be very hard for you to find the right floats if you have a question like, what are all the floats with oxygen sensors in the Pacific, for example. So I will talk mostly about the MATLAB version, but as John mentioned, there's also an R version in a similar toolbox in Python. The workflow looks like this. So first you define your search criteria, which can be many things, spatial, temporally, the variable you're looking for, like oxygen or nitrate, the data mode, and some others. And then you get a report from, when you run this command, you get a report how many floats and profiles were found, and it will also already download the files for you. Then you can do some data exploration, visualizing the data in various ways, maybe adjust the criteria, expand the time or geographic area, or maybe find another sensor, and finally load the data into memory, and then you can do your project, whether it's data analysis, machine learning, whatever you want to do. And now I'll show a quick example. Here I was searching for 5 sensor floats in the Atlantic north of 60 degrees. It found 5 floats, and on the left I show their trajectories, each float colored in with its own color. And on the right is the same version of this plot basically. Here are all oxygen profiles colored by their data mode, with yellow in adjusted mode and green in delayed mode quality control. And you see it took 3 lines of MATLAB to do this. And we have some other plots available. Here's a time series plot example. Here's a vertical section plot for one variable. This is pH. And finally, profiles here with 2 variables for one float. All of these have many options for one float or multiple floats, and some customizations of the plots, and that's far more than this talk is for. So here's the full code for all the examples I showed. You can go from square zero if you never worked with Argo data before, download our toolbox, run these 8 commands, and you have all the plots, you have all the files you need, and you can start working with them. I'd like to acknowledge the work of our contributors. And finally, here are the links for all the toolboxes and some tutorials. Thank you very much.
Great. Thank you, Hartmut. And I will mention that there's a lot of links in there, and then so a copy of these presentations I think will be made available either at the OCB website or also on the GO-BGC website. Or we haven't ironed out those details, but you'll be able to access those links after this webinar. Okay, so I'm going to finish with data adjustment and the resultant data quality. And then so before I start, I want to mention that we hosted a science workshop, a GO-BGC science workshop last year, where we covered how data adjusted in a lot more detail than I'm going to be able to cover today. And then there are videos on YouTube for oxygen, pH, and nitrate, and that goes over both sensor theory and also data adjustment. So if you want to learn more about them, it's on our website, so please go visit that. There's also, we also ran tutorials for how to use the BGC-Argo toolbox that Hartmut just presented, and those recordings are also available on the website. And then so if you want to get started on the toolbox, you can kind of play that video and then walk through step by step. There's even like a tutorial file in the GitHub repositories. So we try to make it as easy and smooth as possible for people to jump into BGC-Argo data. So please check it out if you're interested. Okay, so we went over this before, but there are currently 6 scalable, commercially available BGC sensors profiling floats listed here. And almost all of these parameters need some sort of adjustment before we would consider them, science ready for various reasons. I'll briefly touch on those and how they are adjusted. But going back to what John mentioned, if you're using data from the GDAX, we do not recommend using raw BGC-Argo data because these adjustments need to be made. But if you're looking in near real time, please use adjusted data fields. And then delayed mode is when we go through the data every approximately 3 times a year to do kind of finalize or do a more detailed adjustment. So that's the delayed mode. So when using this data set, you use the adjusted or the delayed mode data. Okay, so all these adjustments, we validate the adjustments by mainly using SOCOM data. So we've deployed over 200 BGC floats. So at the time of deployment, the vast majority of SOCOM floats are co-located with a hydrocast, so with discrete samples. And then so the adjustment data are completely independent of these discrete samples taken at the time of deployment. So by comparing these two, we can assess the quality of the data adjustment protocols that that have been developed over the past 10 plus years. So we will start going through, so the adjustments that we apply for all of these parameters are basically either an offset, which is just a constant value, or a gain, which is a multiplicative correction. So, offset is just, the raw data plus a constant, and then a gain, you multiply the raw data by the gain. And then so some sensors will require one, a gain or an offset only, and some sensors will require both. So I will kind of go through all of them and keep updating this table on the left as we talk through each parameter. So oxygen data. So oxygen, we adjust the data by doing air calibration. So each time the float comes up to the surface, when it phones home, we can also take measurements in the air. And since the Octode has the same response in air and seawater, and we can calculate what the partial pressure of oxygen in the atmosphere is, we can actually calculate a gain factor, which allows us to adjust the oxygen data. And then from this gain, we multiply uncorrected oxygen data with the gain to get the corrected data. So this allows us to improve our accuracy and also assess sensor drift over the lifetime of the float, which is typically under 0.5% per year. And then so how does this do? So this is a property plot of the float oxygen on the y-axis and the bottle oxygen on the x-axis taken at the time of deployment. And you can see it falls, and the black line is the one-to-one line, and then the median residual is about 0 plus minus 6.8 micromole per kilogram. And then we expect some level of natural variability, between the float and the cast samples. And then so we assume about 50% of this variability is due to the spatial temporal natural variability. And then assuming that, we think that the oxygen data set overall is accurate to about 3 micromole per kilogram. And details on these protocols can be found, and the assessment can be found in these two papers, Johnson et al. 2017 and Bauer et al. In 2021. Nitrate and pH, I'm going to lump them together because the data adjustment protocol is very similar. And for both of these parameters, an offset is applied. And so basically, how we assess, how we adjust the data is based on deep measurements where the deep ocean has stable pH and nitrate measurements. And we predict what this reference field in the deep is by using global algorithms such as the Lure series or Canyon Bead. And so by comparing, so each time the float goes down to 1,500 meters, we can calculate the difference between the float measurement and the reference pH or nitrate. And then so if it falls between, in between these kind of accepted, air bounds, then we don't adjust the data at all. But once it starts drifting outside of the bounds, we apply a piecewise linear regression to correct for this drift and then apply a time varying offset correction. It's not uncommon to see jumps in data like this due to maybe optical, things getting caught in the optics of the nitrate sensor. And so that is why we do a piecewise linear regression, so we can account for these jumps. So after applying this data adjustment, this is another validation plot of nitrate on the left and pH on the right. In the statistics, the median residuals for nitrate is about 0 plus or minus 1 micromole per kilogram, and pH is about 0 plus minus 0.015. And using the same logic, that assuming half of this variability is due to spatial temporal variability, we think that the nitrate and pH data are accurate to about 0.5 micromole per kilogram and about 0.007 for pH. And this, I don't have the N, but these are, hundreds or maybe thousands of discrete samples for each of these parameters. So, okay, moving on to chlorophyll A fluorescence. So the sensor measures fluorescence and we convert it to chlorophyll A concentration because that's what we are interested in. And in order to do that, there are basically two corrections. One is the bias correction or the offset, where we account for the dark counts, and we do that by looking at the deep data. And then in order to go from this fluorescence to a concentration, we have to multiply by a scale factor. And this is where the gain correction comes in. And currently we apply a scale factor of 2. And this is based on comparisons of fluorometers and HPLC samples taken around the world. And this, we chose 2 because based on results from Rossler et al. In 2017, where they claimed, where they demonstrated that the global average of this correction factor is about 2. But you can see that there is a large variability, and this scale factor can range from about 1 to 6 globally. We have also assessed this through the SOCOM data as well. So this is a histogram of the gain correction based on the float versus HPLC samples taken at the time of deployment. And then the mean is about 5 years. So you can see that there's a big geographic variability. And then so the global average of 2 might not be, might lead to systematic biases depending on where you are looking at the data. So we strongly encourage anyone using chlorophyll concentration to look into these issues before completely trusting the concentrations. There's also an additional correction for non-photochemical quenching. Fluorescence decreases during the daytime. So to correct for that, we use a protocol outlined in Zing et al. In 2012, basically, where we find the maximum chlorophyll value in the mixed layer depth and then just assume that it's constant in the mixed layer. So that is an additional correction that we apply for the chlorophyll A concentration data that we report. Okay, running out of time, but we're almost done. And then, so the last sensor for the backscatter and irradiance, these sensors actually require the least amount of correction. They both require a small 0 correction, and they're both based on measurements down in the deep ocean where there's not a lot of activity going on. But other than that, we don't adjust data for either of these sensors. So these seem to be very robust and stable over time. So these are the good ones. So anyways, that's all I had. And I know, sorry, that was a kind of a fire hose of information, but again, I want to reiterate, like, all of this was covered in much more detail in the science workshop, and the videos are available. So if you're interested, please check them out. Yeah, so with that, I think we can start discussions. Okay, so there is a question by Connor Tate. Are there any project scientists using the float data to propagate data in simulated environments for machine learning and algorithm training purposes? I might let John take that one.
Let's see. I saw that Lynn put an answer in talking about yeah, I don't know if everyone can see that, but talking about how SOCOM data are used in state estimation. So in the BSAUCE, the Biogeochemical Southern Ocean State Estimate, uses SOCOM data. As far as, let's see, simulated environments for machine learning and algorithm training purposes. I think there are efforts underway, certainly to start using float data in training new algorithms, training machine learning algorithms for producing, Alison shaking her head, I know she's doing some of this, for producing data products. I think there's some interest in potentially incorporating float data into the algorithms that are used for estimating, like the Esper and Lyra algorithms for estimating oceanographic parameters sometime in the future. So those kinds of things are underway. And as Lynn said in her comment as well, the more efforts on this, the better. When more people start doing these kinds of things, we can start intercomparing and kind of honing in on the best methods to use float data for these purposes.
Great, thanks, John. There's a question that I really want to address by Denise Hernandez, and it says, does every BGC deployment require a CTD/bottle sampling for calibration? And the answer, and so the validation, the comparisons that I showed are completely independent of the data adjustments. So the answer is no, we don't. And then we, in fact, we routinely deploy floats without rosettes. And that will just become a necessity when we're trying to reach a global array, because we can't expect that every single BGC float will be deployed off of a research vessel. And that's why we have independent methods such as air calibrations or using these deep reference to adjust the data. So we strive to get as many floats onto cruises that conduct high quality hydrocasts, such as GO-Ship cruises, but we cannot create a global array that way. But those discrete samples serve an extremely important purpose of validating our data adjustment protocols. And so I just want to emphasize those are really independent. It really is an independent way of validating our adjustment. So, and that's extremely important as we expand our BGC deployments in different basins around the ocean. Great question, thank you. Okay, can I ask, will MATLAB Toolbox work in Octave? I don't know what that is, but Hartmut responded, I have not tested, but we'll get back to you.
It's basically free MATLAB.
Oh, got it. Okay.
But probably stripped down, so I will have to test if that works.
Great. Thanks.
Oh, there's a free MATLAB. Thank you.
News to me, yeah. So, okay. Well, hopefully it will work.
Yui, this is Heather. There's a question in the chat, a related question to the last one about whether or not if it's indicated in the metadata or somewhere if an Argo float has had an air calibration.
Yeah, that's another good question. I'm actually not sure if, so not all floats can do, not all oxygen sensors can do an air calibration. For example, Seabird 63s, they are in the pump flow stream of the CTD, so they don't get exposed to air when they come up to the surface, so they don't get a correction, or they don't do an air calibration. So there, for those floats, we can do different ways of adjusting the data. If there was a hydrocast, then we could correct it to the Winkler samples upon deployment, and that upon deployment. Or alternatively, we can correct it to a global climatology. We use the World Ocean Atlas to look at the mean gain correction, and that approach we think is accurate to about 3%. So depending on how, but if the field is not raw but underscore adjusted or delay mode, then some sort of adjustment has been made to the oxygen data. And then so I don't think we explicitly say what was applied, but the uncertainties for the oxygen measurements will change according to the method that we use to adjust the data. So if you're interested in that, I'm actually not sure where that uncertainty lives in the SPROF files or in the meta files, but maybe John or someone else knows, but it is included in the Argo data. John,
Even.
I was going to send it to Yubin.
Okay, I can take a question regarding how to further identify whether the Argo has a air calibration mechanism. If you download the S profile, there is a variable called the scientific calibration column. In this variable, they have clear mention how the oxygen is calibrated. For example, if it was calibrated by the World Ocean Atlas, they will mention it, the gain factor is derived from the WOA. Otherwise, they will say that the oxygen is calibrated by the air measurement. John, do you have any point you want to add?
Great, thank you so much. There's another one. In terms of public data archives, is there one that gathers all BGC data sets? Or I want
Argo.
I want to if you want the most complete gathering of BGC data, do you have to query several archives? Lynn, do you know?
I would say the answer is that the Argo GDAC would have the complete collection, but you're not going to get the derived variables there, derived carbon. There you need to go to individual projects.
Yeah, and I wasn't
Is
sure if
that
this
correct?
That's
most of
correct.
you?
Yes, absolutely. If you're only looking for BGC float data, but I wasn't sure if the question was referring to, you know, all BGC data from ships and all of that. And then for that, I think you have to create multiple archives.
Yeah.
I don't think there's any, not that I know that, you know, consolidates all of these parameters from ships and
Well,
glasses.
NCEI has everything, but ultimately,
Mhm.
yes, that would.
Is 1,000 meters a standard drift depth for floats deployed in all regions? Or can it vary from region to region? Alison, do you want to take this one? Or I think I know the answer, but
Is 1,000, sorry, is 1,000 decibars the standard drift depth? That was the question, right? Yeah, for the GO-BGC and SOCON floods, it's definitely true. That is the recommended parking depth for Argo, at least the 2,000 decibar floats. So I would say not every float out there may be parked at that depth, but that is the majority of them are.
If they're Argo, they should be 1,000. There are
Yeah.
many other BGC floats, and it's encouraged to write proposals and get BGC type floats for your experiments in regions. And then you may have a much faster, a different parking depth and a much faster profiling, or different profiling, different sensor suite. Those are not eliminated by having the BGC Argo program.
great point, Lynn. This is a very important question. What is the difference between the adjusted and delayed mode data? What processing is applied on both? And then so the real-time adjusted data, you know, does the, you know, the drift correction or the error calibration corrections in real time, but it doesn't use the most recent, you know, like the drift correction. For example, if your sensor is drifting at, let's say, 1 micromole per kilogram per year, for the delayed mode, we look at those trends and then try to do a correction, and then that happens 3 times a year. But then, you know, between those, you know, 4 months between the delayed mode, the float keeps reporting data, right? And then so we don't actually extrapolate out the drift. We just take the most recent point that we did the delay mode correction for, and then just use that as a constant value over time. So that's the difference between real time and delayed mode. A real-time adjusted and delayed mode data. And the uncertainties will be different between these two reported values, and then they are also reported in the Argo files as well. So they're, you know, so we try to account for the, you know, so the real-time adjusted data will have higher uncertainty than the delayed mode because we haven't had, you know, we don't apply a drift correction for the most recent 4 to 6 months. So that's the main difference. Another question, are there any Gulf of Mexico partners that you work with to deploy, maintain, or pursue new research with the floats? Well, so we have floats in the
Maybe Alison can answer that.
Oh yeah, sorry. I was just gonna say that, yeah, that we have deployed working with NOAA AOML is working to deploy floats in the Gulf of Mexico. BGC floats. There
are several in there now, right? Four operating. Emily Osborne.
Yep. So hopefully that answered the question.
The data is available in real time as well. So if you're interested in the Gulf of Mexico data, use the BGC-Argo toolbox and download it. Yeah. Another question. Are the uncertainties in the data good enough currently, or do they need to be tightened? Let's take this one.
Well, I can say maybe something, which is that I guess the answer to that question is depends on what your application and what your requirements are. And I mean, I think everyone that works with sensors would always say you can make improvements and then reducing the uncertainties. And I think there's, that's active research is improving the sensor quality. But I think for many applications, the uncertainties that our estimate of the uncertainty for the current generation of floats is probably adequate. So I don't know. I think it does. Bottom line is that it depends on your application. I don't know if Yui or Len or anyone else wants to add anything.
I will add one kind of subtle point in that, like, so the uncertainties that we provide are kind of the accuracy, right? And as if you compare float to float, what kind of variability, what's like the range that we think, is, the true values encompassed in. But there are other applications that don't necessarily rely on absolute accuracy, right? So if you're looking at vertical gradients, for example, or temporal gradients from a single float, then the uncertainties become smaller because the errors are correlated, right? And then, so, for the whole profile, it might be off by 1%, but if you're interested in looking at the difference in oxygen from 100 meters to 200 meters or something, you'll be able to determine that with much higher, precision or accuracy than the overall uncertainty. And then, so it's kind of important to think about, again, your application, right? And then whether or not some of those, uncertainties will get reduced or not, and so that's something that I think each researcher needs to think about a lot before really using the data. There's a question in the chat. Are there any plans to use the float data for value-added products? For instance, vertical eddy diffusion coefficients, microturbulence, etc. I'm just thinking out loud.
Mm-hmm.
Definitely. Yeah, and I think those are very creative uses, or applications of float data. So if you want to look at the vertical, ascent rate variability to look at turbulence, for example, people have done that using the deep ocean. So Caitlin Whalen's work has looked at internal wave dynamics, I believe, looking at deep Argo, deeper measurements. So yeah, it's not something that we are actively I think those are research topics. So anyone, if you're interested in that kind of stuff, we should strongly encourage you to pursue it. Is Argo flow technology cost effective for coastal studies? Is there any need for developing cheaper versions? Take that. Well, I can take that. So profiling floats are not designed to work in the coastal ocean. So they, because they tend to wash up on the beach, so, and then so it depends on how coastal you mean, but so we would need different platforms such as, gliders underwater gliders are a good platform that are designed to work well in the coastal ocean. They can play an important role in connecting the open ocean measurements made by profiling floats to the coastal ocean made by, I don't know, moorings or whatever, so different, I think, platforms will fill that role. Is there any need for developing cheaper versions? Yeah, of course. We want cheap, the economy of scale, but yeah. We are always working on that. So it is past 11 o'clock. I don't know. There's 2 more questions, so let's just go through that and then we'll call it a day. Is anyone working on extracting the CDOM data from the ISIS spectrophotometer, since this is the biggest signal subtracted to get nitrate? So I know there has been some work looking at that in the coastal ocean, but actually the biggest signal in the UV absorbance spectra is bromide, not CDOM. And we use the linear parameterization to kind of subtract out the CDOM data. But I'm not sure. I don't know if anyone is actively working on trying to extract CDOM from the absorbance spectra.
CDOM is, I mean, I've seen CDOM in the variables, so I don't know how they did it, but it's certainly there.
Yeah, so one of the fluorescence sensors, it has a CDOM channel. So there, yes, I forget what the excitation wavelength is, but there's a CDOM channel. I think that is very underutilized. I think people are still trying to figure out what we can do with the CDOM data. So I think that is a field that is, I think can be tackled with, and yeah, whoever's really motivated and creative, please figure out what to do with the CDOM data. Okay, the last one. Can you explain how we can access ascent rate data?
I'm not sure if that is regularly supplied for all Argo floats, but it would probably be in the technical, their tech files in the, or maybe in the metadata files, which are part of the GDAC for every float. So I could be wrong, but my understanding is that is not necessarily recorded for and provided for every float. Every float type is different a little bit. So yeah. If you have more specific questions, you could get in touch or.
Cool. Sorry, I promised two, but one last one. So I think this is for you, Hartmut and John. There's a Google Colab tutorial for interacting with data on your GitHub. If we run across errors, is there a current contact we can reach to ask for specific questions about the Colab? And maybe that was.
Yes, I posted that in the chat.
Oh, you did?
Ethan Campbell at UW.
Thank you. Sorry, I didn't see that. Thank you. Well, we are a little bit over, so I would. Is anyone else from the panel want to make some concluding remarks?
I just want to say thank you, Yui, for leading today's webinar, and also that just to remember that if you have suggestions for anybody who would like to see give a webinar in the future, please let us know.
And thank you everyone for attending our webinar. And this has been recorded, I believe, and it will be posted on the website. So thank you very much, and yeah, thanks for joining. Please use BGC-Argo data.